In this video, I'm going to discuss a bit of the math of Hardy-Weinberg equilibrium. The first I'm going to cover is allele frequency. And so allele frequency is how frequent a certain allele is in a population. And so the dominant allele, we'll use capital A, or the recessive allele. And frequency is sort of like percentage, except for it is just a decimal. All right, so for example, 50% would be 0.50. So the percentage is everything after this decimal place. So it's just like a percentage. It's a frequency, how frequent something is. So allele frequency, we're going to do the number of copies of that allele in the population divided by the total number of alleles in that population. So for example, if a population has 15 homozygous dominant individuals, 30 heterozygous individuals, and 15 homozygous recessive individuals, to know how frequent the capital A allele is, there's capital A alleles, there's 2 of them here, and 1 of them here. So I need to take the number of homozygous dominant individuals times 2, so I'll do 15 times 2, because each of those 15 people has 2 homozygous dominant alleles, plus the number of heterozygous individuals times 1, because each of those heterozygous individuals has 1 copy of the dominant allele, divided by the total number of individuals times 2, because that's how many alleles everybody has. So the total number of individuals is 15 plus 30 plus 15, that makes 60 times 2. So this gets me 30 plus 30 over 120, which I'm going to just go to the side here, up this way, is 60 over 120, which actually ends up being 0.5. I didn't even think. So that is the frequency of the capital A allele. I can do the exact same thing with the lowercase a allele if I wanted to, except for instead of doing homozygous dominant, I would do homozygous recessive individuals. So we can give these allele frequencies symbols. A lowercase p, and capital and lowercase matter, lowercase p is the frequency of the dominant allele, and lowercase q is the frequency of the recessive allele. And a lot of kids mess those up, so you need to make sure you know p is dominant, q is recessive. And so the first of 2 main equations for Hardy-Weinberg equilibrium is p plus q equals 1. And again, this makes sense because the dominant A and the recessive A are the only alleles, and so the total frequency of those alleles must add up to 1 or 100%. They're the only things that exist. So if they don't add up to 100%, that means I haven't counted them right. So p plus q equals 1. The second equation is p squared plus 2pq plus q squared equals 1. And this is just, so here we were talking about the alleles, and in this equation I'm talking about genotypes. P squared is the frequency of the homozygous dominant genotype. 2pq is the frequency of the heterozygote genotype. Q squared is the frequency of the homozygous recessive genotype. Think about it this way. 2 p's, and those are 2 dominant A's. We said P is dominant A. P and Q together is heterozygous. Again, P, Q together. And 2 Q's, 2 recessives. That's how I remember those. As opposed to allele frequencies, there's now genotypic frequencies. So for example, how many individuals, or what's the frequency of this genotype or that genotype? And again, it makes sense that all of these frequencies add to 1 because these 3 genotypes are the only options they have. Therefore, the total of all of those things must add to 100% or 1. So here's an example problem. You've sampled a population in which you know that the percentage of homozygous recessive genotypes are 36%. Use that to calculate the following. Okay, so when it says the percentage of homozygous recessive genotype, I know that that is q squared, but I don't want it in a percent, I want it in a decimal, so I just divide by 100 and I get 0.36 is my q squared. Then I am getting the frequency of the A allele, which is q. So if I have q squared is equal to 0.36, I can just square root both of those items and get Q is equal to the square root of 36, or 0.36, which is 0.6. So I have now this one, 0.6. Now I want the frequency of the capital A allele, which is P. I know that P plus Q equals 1, and so if I substitute in Q, I now have P plus 0.6 equals 1. So P must be 0.4. And lastly, now that I have P, I can get these two frequencies. Therefore, P squared is just squaring both sides. 0.4 squared is 0.16. And 2PQ is literally 2 times P times Q, so that's 2 times 0.4 times 0.6, and that equals 0.48. So that's 2PQ. This is Q squared. And if I want to check my work, I know that P squared plus 2PQ plus Q squared is equal to 1. So let me see. I have 0.16 plus 0.48 plus 0.36. Does that equal to 1? Let me put this in my calculator. Yes, it does. So I know that all of this is correct.